Hi everyone, today I would like to present our automated control system simulation developed in Proteus, as shown in this video. The core objective of this project is to implement a sequential state controller that monitors specific numeric threshold to trigger external hardware outputs, specifically status indicator LEDs and DC motor drive circuit. This type of architecture is widely used in industrial automation, automated assembly lines, and time process control. Let's break down the key hardware components that make this system work. The brain. At the center, we have PIC 16F84A microcontroller. It executes the embedded logic managing the timing and I/O states. It is supported by an external crystal oscillator circuit for accurate clock cycles. The display system. To handle the visual readout without exhausting the microcontroller's I/O pins, we utilize two 74LS47 BCD to 7 segment decoders, U2 and U3. These chips take a 4-bit binary coded decimal input from port B of the PIC and convert it to the drive, the common anode dual 7 segments display. The actuation and indicators. On the bottom left, we have a green LED and a red LED for status monitoring, alongside a DC motor driven by a TIP120 Darlington transistor and protected by 1N4001 freewheeling diode to handle inductive back EMF. Now, let's observe the operational behavior of the system as demonstrated in the simulation. Initialization. The system starts at a baseline state of 00. State progression, the system sequence quickly shifts to 15, progresses to 50, and then moves to 75. During these stages, the system is in a holding or preparation phase. The red LED remains active, signaling that the primary process, the motor, is idle. Threshold reached 90. Once the display reaches the critical threshold of 90, the logic conditions are met. The microcontroller immediately drops the red LED signal, switches the green LED on, and sends a high signal to the TIP120 transistor base. After executing its active cycle at state 90, the system loops safely back to 00, turning off the motor and green LED, resetting the sequence. In conclusion, this simulation successfully demonstrates how firmware running on a PIC 16F84A can seamlessly coordinate digital logic decoders for user feedback while simultaneously managing power electronics to drive mechanical loads. The circuit is highly scalable. By simply adjusting the firmware code, we could change the numerical trigger points or alter the motor speed using pulse width modulation (PWM). Thank you for your time.